All right, so let's look at the information necessary to complete the 4C lab for batteries, resistors, and currents. So we're going to look at some simple circuits with batteries and combinations of wires and light bulbs and see what we can determine from these things. So we have a formula called Ohm's law, that the potential difference or voltage across the circuit is equal to the current through the circuit multiplied by the total resistance of the circuit. And then we can take this and we can also apply it to individual resistors, which in this case will be light bulbs. And ohm, named after, the guy from Ohm's law, is the Greek symbol omega, capital letter, kind of looks like an upside down horseshoe, and that is technically a combination of a volt divided by an amp. Okay, so useful information like we generally have with the introductions. If we have resistors in series, then in series means all in a row or in a particular order, kind of like a TV series or Netflix series or World Series if you're talking about sports. So the resistors are in order. Current goes through all of them, and so the total resistance or effective or equivalent resistance, different words for the same thing, is just the sum of those individual resistors. Now in parallel, then what happens is a portion of the current is going to go through the different loops or different options in a parallel circuit. We're going to see those a little bit further on, but because it's a portion of the current, then what happens is there's a portion of the resistance that factors into each different place. And so unfortunately, we get a more complex setup where it's 1 over the effective resistance or equivalent resistance is equal to 1 over each resistance, and then the sum of those. Then power formula, I'm not sure if it has any other fancy name, is the current multiplied by the potential difference. And then if we slightly rearrange what potential difference means from this formula over here, combine them into each other, then we get the current squared times the resistance. So that's something that we're going to use in a few places. Okay, so let's move on. We have our circuit that we're going to build into here. So we've got 3 of what look like either C or D batteries that we're going to plug into the battery slots here. And the way the wires are run, these are all in series, so they're going to add up to make more voltage. If these are C or D batteries, most disposable batteries are 1.5 volts. And so if we have, say 3 of those together, then we can estimate what that's going to be. So next question, I'm not going to tell you, but like I said, if each of these is 1.5 volts, like most disposable batteries, and there are 3 of them, I think that's something you could figure out. If you have trouble, like always, read the hint, try again. Okay, then direct current is what we typically get from batteries. So the multimeter is going to have the settings set for that. And then we're going to use that to eventually read the current that runs through. So this is MA for milliamps. So we need to remember what milli means when it comes time to take a reading from this. Okay, so all we need to record so far, from earlier, we had 3 times 1.5 volts, and then that's where the 4.5 volts comes from. So hopefully that's what you guessed on that question. All right, so next phase, we're going to start to build with these. So we've got light bulbs in different places, and we're going to put them, and depending on the setup, in 1 to 4 different slots, and then fill in wires in different places to complete circuits. So we would take the light bulb, put it in for position A, then we're only interested in having 1 light bulb. So we're going to fill in wires around this way to complete the circuit. So in the end, it should look something like that. It's not going to turn on at first. So if you feel like it's broken, if it's not giving a reading, if the light's not coming on, remember to close the switch. So here it was open, here it's closed, and that's where we get our reading. Okay, so then we want to determine the resistance of the light bulb. So you want to remember that we said Ohm's law was V equals I times R. If you want the resistance, if you're looking for R, then we're going to have to divide the current away. And so we can say that the resistance is the potential difference divided by the current. Well, we happen to know the potential difference is 4.5 volts, and it should be for everybody. What's going to change is your current. Now, remember that this is milliamps. So if you want to convert that, then what's going to happen is milli means 1,000th piece of So we would bump 1, 2, 3 spots over, and that becomes 0.0978 amps. Okay, so then that's what would end up dividing here. As directed in the introduction, and you can check back to that if you want to, if we take a volt divided by an amp, then we get an ohm, and so that matches what we're looking for a resistance. All right, so let's check this power number. We've got P equals I squared times R. So for us, I, remember this is milliamps now, so you want to convert to regular amps. That's going to be 0.0978 amps that gets squared. And then the R is the 46 ohms. Then when you calculate this, you get 0.43998, so on, which rounds to 0.440. Now for the units, we have an amp times an ohm, which turns into a volt, and then a volt times another amp turns into a watt, so that measures the stuff that we're looking for. And then the lab forces us to clean up our mess, so we have to open the switch and take the pieces out and put them away, and then that's the end of the phase. Okay, so in the next phase, we're going to look at resistors in series. So having more than one light bulb in a row, like this. So we have light bulbs for A and B. D is completed by just a wire to make sure that this is all connected. There's nothing for C yet, and there we go. Notice that our current is a little different this time. You might even notice by what factor, but for right now, we're just going to notice that's lower, and then we want to run through and see what we think. So given that these are in series, and there's only one way around that the current can go, then I think that's probably a pretty good clue for what the answer needs to be. But if you're not sure, make your guess, read the hint if you need to, try again, and then see if it makes sense once you for sure know the answer. For the next part, we're going to do similar calculations to what we did before. So our predicted resistance, because these are in series, and we were told in the introduction that in series they add together, then we expect that we have 46 plus 46. Technically 0.0 in proper decimal places, but I don't have a lot of room here. The current is 48.9 milliamps. So again, you want to remember that that's going to move over 3 times once we convert these to regular amps. And then we can find the experimental resistance there using a similar approach to last time. So give that a try and see if it works the way you expect. These numbers should match, or they should be very, very close depending on your random numbers, but they should be near enough to each other that you trust that it's correct. Then from there, remember the power, you've got P equals I squared times R. So we've already seen one of these examples. I want you to try it this time. If you get stuck, send me an email or send your instructor an email. But I think you can do it given our other information. We would have I, we would have R. Remember, this I needs to be converted, but we did that over on the multimeter. So I think you can finish this part. Something to keep in mind is that compared to here, our answer was 1/4 of what it was before. So see if you can think about why maybe that happened. And once more, we have to clean up our mess before we can move on. So open the circuit, remove the pieces, put them away, and then back to a clean table. Okay, so now in parallel. Parallel, you know, the little L's in this are sort of a clue, means things that run next to each other. Well, that can't be for A or B because those run in order, but if you see C is an option, D is an option, then hey, there you go. So hopefully that's what you guessed. What might be a little bit surprising here is that we have 2 light bulbs again, but the current actually went higher, right? So this is bigger than the numbers that we had before. So for use later, we're going to want amps. So remember, milli means 1,000 pieces. So if we divide this by 1,000 and move it back, then be careful of 0.1957, right? There's more digits in this, and so moving around, we don't have any additional zeros in front, just the one by the decimal place. Okay, then what we want to think about here, when this potential difference created by these batteries is trying to push through the circuit, it's going to hit this point now, and it's going to do something in two directions. Well, as it turns out, the current loops are going to have the same potential difference. So you're going to see 4.5 volts this way and 4.5 volts this way. So that's where the word parallel kind of comes in and means something, is that you basically have the same circuits running next to each other, right? And it makes sense with the light bulbs running next to each other, but they actually see the same potential difference as we had here, which I guess means I accidentally spoiled the question, but hopefully you were thinking about that anyway. Thinking about whether the light bulbs were brighter in parallel versus series, again, make the guess if you need to, but think about the current we had. That's a little bit covered up, but this is a higher current. So think about what having a higher current would mean. Or I suppose we could look at the picture. You can kind of see the shape of the light that's coming around it. Whereas here, I feel like that's potentially a smaller shape. Maybe that means something. All right, then for our calculations here. So something strange happens when we're in parallel. You want to remember that your resistance, it's all dealing with reciprocals. So 1 over R is equal to 1 over 46. That's from, I had to find it, that's from up here, plus 1 over 46. Now this is simplified quite a bit because these are the same resistance light bulbs, but that's going to give us 2 over 46, which is 1 over 23. And at first glance, you might think, hey, well, that's wrong because this just says 23. But you need to remember that this is the 1 over the resistance, and that's 1 over 23. So if I have 1 over R equals 1 over 23, technically, if you wanted to, you could treat that like a proportion. And if you cross multiply it, you'd end up with just R equals 23. So interestingly enough, if you have exactly the same resistances and you put them in parallel, then you get half the total resistance at the end, or half the equivalent resistance at the end. The reason it works that way is because there ends up being more than one loop for how the current can go. So the current can go here and some more of the current can go there. And basically there's just more ways for currents to move. And so they can do so more easily and more at a time. All right, so let's go ahead and look at this next part. So we need to confirm our resistance first. So we want to remember that R is equal to V over I. So rearranging Ohm's law will give us this. The potential is going to come from the batteries. Remember, each one's 1.5, so it's a total of 4.5, which we had listed up at the top. And then for the current, 195.7, but remember these are milliamps. So the decimal will bump 3 times. You can divide that by 1,000 to change it manually. 0.1957. And that should come out relatively close to 23.0, which is basically what we're looking for. So that looks good. Then we need to remember for the next part, the current at C or D. So not the total current running everywhere, but the current running through either of the paths. Because they have the same amount of resistance, then that current that we had earlier is going to split and move evenly between those. So we would divide by 2 from the total, get approximately 97.9 milliamps going in each direction. Then that's going to be important for how we set up when we find the power dissipation on this last part. So P equals I squared times R. And remember, we're looking at one light bulb at a time here, not the full values for the circuit. So for the one light bulb, the 97.9 milliamps divided by 1,000, or bump the decimal 3 times, is going to be 0.979 amps squared. Then the resistance of the bulb, of the one bulb, is 46 ohms. So as a pair, because of the way parallel bulbs work, the overall resistance is lower, but for the individual bulbs, we do have still the 46 ohms. Then multiplying those together, like we saw before, an amp times an ohm makes a volt times another amp makes a watt, and we actually get the same answer for watts that we saw earlier. So same as having an individual bulb, they're just running next to each other, which again matches that word parallel. So series and parallel, we're going to fill in all the light bulbs we can fill in. So we don't need any wires this time because we populated every space with a light bulb. So notice that these light bulbs are in series with each other, these are in parallel with each other, and in the circuit we end up having both options. Your usual strategy for these is to see what these would be as an equivalent resistance. So if they were one light bulb instead of two, what would that resistance need to be to act the same? And then basically after that, you make them all series and put them all together. So what's interesting here is that from earlier, one light bulb was 46 ohms of resistance. And when they're in series, they keep the same thing. But when they're in parallel like this, what ends up happening is if they were put together, when we look at them as one unit, then it's half of this value. So I know it's strange. We've got two light bulbs. You would think the resistance would go higher, but they actually go lower whenever they're in parallel. So mathematically, it works. Thinking about it, it seems strange, but we'll make it work. Okay, so think about this one. Give it a try. We've seen the picture. Just think about it. All right, so let's work on confirming these values for the next part. So we have these in series and parallel, and so we want to remember what that's going to mean for our resistances. For the bulbs in series, or any independent bulb on its own, if we look in just one place, is going to be 46 ohms. Then we have two of those. They're hidden by the picture right now, but there's one here in series. So 46 ohms for each of those. And then we need to remember that in parallel, that these work kind of funny, that as a pair, because they're the same and they're in parallel, we actually end up getting half of the resistance when these get combined, which I know sounds completely funny, but with the way that the current splits and goes in different directions, the overall resistance goes lower. We can actually see that we had a different amount of current here compared to what we would have expected to see earlier and what we're going to see later. So adding those together gives you your 115. So the current, read straight from here, 39.1 milliamps. When we go to find the resistance, we want to remember that resistance is equal to potential divided by current. Your potential is going to come from the three batteries, which are 1.5 volts each. So it's 4.5 volts. Then the current for the whole circuit, remember, is 39.1 milliamps. So we need to convert that first. 0.0391 amps. And then that's where we're going to get our resistance, which matches pretty closely, off by around 1% given all of this. Okay, and then now as we're working down a little bit further, so it talks about the current running through C or D. So we need to remember that at this point, the current's going to split and it's going to go this way and it's going to go this way. Because these are the same resistance light bulbs, they're going to see the same split, an even split on the current. So where we had 39.1 milliamps for the full circuit, that's going to split from here and basically rejoin later. But through this one path, we're going to have 39.1 milliamps divided by 2. From the other path, we're going to have the same amount divided by 2, right? And so plus or minus a tiny bit of rounding gets us this value here. Then now we want to work through these different power formulas. Remember that P equals I squared times R. But you want to make sure you're matching this up. So for the ones in series, you're going to have the same current as the whole circuit. So you're going to see the 0.0391 as the current, and then the resistance is going to be 46 ohms, because anytime we look at any individual light bulb, we see 46 ohms. Then you would do the same thing on the next one, and I'm going to leave these full calculations for you because we've done a handful of them. I think you can do them. If you have any trouble, email your instructor and ask. We want to remember that the current from C and D is different, right? That's the 19.6 milliamps, or 0.0196 converted to amps. And the resistance is going to be 46 again. If you're looking at one bulb at a time, it's still that same 46. So give that a try. If you get stuck, let your instructor know, but I think it's something you can handle. Okay, this one, we don't even have to clean up our mess. We move on to the next phase. So what we're going to do now is, while this is still running, we're going to make some small adjustments, and we want to see what's going to happen. So it says here, bulb D is removed and not replaced by anything. So we open and we make a gap. And then we want to see what changed. Okay, so I've done this a few times. I think you can see why this part makes sense. So bulb A or B will end up getting dimmer. Those are the ones that were originally in series and are now still technically in series. And then bulb C actually got brighter. So C and D were in parallel before, but D just got removed with no other connection. So C is now brighter. What's going to happen, and the reason why that worked, is from before, the current was splitting and going this direction and this direction. And then when D is taken out, there's nothing here, and basically all of that current's going to loop and go this way. So that makes C brighter. Then what's strange about this is that you have fewer light bulbs, but you actually end up with more resistance, right? So look, we can see that with everything in there, this was 39.1, and then, oops, I went the wrong way. But with only 3 light bulbs in here, we have less current. And so the reason why that happens, there's fewer paths around for the current to go, and basically there's less of a way for the current to avoid resistances. And so now this is like 3 of these in series because nothing's going to go there. And so these just add to each other and they become a bigger number. So we had a resistance of 115 when we had series parallel, but when it's 3 in series, it's going to be 46 times 3, which is 138, and that's a bigger number. So A and B got dimmer, and C got brighter. D is obviously no longer in there. Okay, then for the next part, we are going to remove bulb D, but then we're going to replace with a wire. So in this case, notice that we took the bulb out and then we made a straight line there. So C is interesting. C basically gets just turned off. Okay, so when we think about that, we had current that was splitting and going this way and this way. When we take that bulb out, technically this current still split and go the different directions, but because it's so much easier for the current to go around this way, a whole bunch of it does, and essentially none of it's going to go that way. In the bulb, a really huge factor compared to the almost zero resistance that's in just a plain wire. Okay, then if we look at the overall current here, because basically it sees zero resistance going around this way, then overall the resistance goes lower, which means overall the current goes higher. And so, oops, we look at A and B, they go brighter. Okay, then technically in a real lab, we want to tear this down and put everything up, but instead in this virtual lab, we're done. Congratulations. So like any of the other ones, if you completed everything, then you get a congratulations screen. If you didn't complete everything, then you get a less than 100% for what you did complete. So hopefully you got through everything, didn't run out of time or get hit by the due date, or didn't submit early, then you got a congratulations screen. But that's it.